Okay, it's time to start, and today we will finish the greedy paradigm, or at least we plan to finish greedy paradigm with some another graph theoretic problem. What we have seen in this course already are some scheduling problems. We started with interval scheduling, then we moved to minimizing the maximum lateness time. And last class we saw minimum spanning tree. We saw some different approaches to solving minimum spanning tree. And today is the last one in this greedy paradigm, which is shortest path problem. Okay, it's a very well studied problem, and we still don't have a complete understanding of the time complexity of shortest path. It's a very active research area. So what is this problem? You are given a graph with vertices and set of edges, and it might be directed or undirected, meaning there could be directions on the edges. So the edge, if you are given an edge uv, the edge might be directed from u to v or v to u or both. Okay, and it is an edge weighted graph. Let's say this w of e denotes the weight of the edge u. Okay, and what we are interested in is this problem. Given a source vertex and a sink vertex, S and T, we want to find the shortest path from S to T, right? So what we want is a sequence of edges starting from S and ending in T, but the number of such edges or the total weight of the edges, that should be as small as possible. Okay. So this is one problem where we are given the source and the sink vertex. Another useful problem is, which is you are just given the start vertex and you want to find the shortest path from S to all other vertices. This is known as the single source shortest path problem. And There's yet another problem, which is finding shortest path for all pairs of vertices. This is more popularly, we'll refer to this as AppSub, right? So it's known as the all pairs shortest path. And all three of them are widely studied. And this problem has quite a few applications depending on what you consider your vertices and set of edges to. Okay. So for instance, this AppSub problem, which is finding the shortest path for all pairs of vertices. One potential application is Google Maps, right? You want to go from one place to another. So Google keeps on receiving all these queries and they don't know beforehand which query is going to come. Okay. And so ideally what is done is they store beforehand all the shortest path for all pairs of vertices so that whichever query comes can just process it and apply this algorithm and return the shortest path. Okay. Actually, it is much more complicated because Google needs to keep track of traffic conditions and so on. But we'll not go into that for this class. We'll just assume that assuming everything is constant, all traffic conditions, the map, and there are no new paths or no new roads are being cut off, right? There is no entry or anything. So we are just given this map, which you can model it as a graph, and you know the distance between a pair of cities, and we want to know what is the shortest path to go from one city to another. Okay. This is one application. Another comes in this web page routing. Okay. You are browsing the web, and let's say, and there are many links between these web pages. So in this case, so the Google Maps thing was undirected, right? Because if you can go from one city to another, you can also come back from the destination city to the source city by following the same route, right? So that graph is undirected; it doesn't have any directions. In the web page routing problem, let's say you want to go from one web page to another, and there are various links which link from one web page to another. And we want to know, we are given two different web pages and we want to know what is the shortest path from one web page to another. Okay. And there are many other tons of applications. Okay. You can consider your vertices to be something, model the edges to be something. Graphs are useful, and that is why we pay a lot of attention to graph algorithms, is because they can model many relationships between different things. Right? So this is why graph algorithms are studied quite a lot. And let's see how to solve this problem. We will see all three of them. First is we want to find the shortest path from S to T. Okay. And second is the single source shortest path problem. The shortest path from S to all other vertices. And this is the all pair shortest path problem, which is finding the shortest path for all pairs of vertices. And in fact, we don't have a complete understanding of any of these things. We are still searching and quite active research area. And okay, so we'll start with some definitions and terminology, which we'll use again and again. We are given a directed graph. So we are given a set of vertices, set of edges, and there are these edges are directed from one vertex to another. And we are also given some weight function. Okay. So every edge, there's a mapping from the set of edges to the set of real numbers. Okay. Some cases, the graphs are simple, like the edge weights are only integral weights, and you possibly have some simpler algorithms. But let's assume that you are given some real weighted graph. And let's say we have this path P, which goes from V1 to Vk via an intermediate set of nodes. Right? Goes from V1 to V2, V2 to V3, and so on from Vk minus 1 to Vk. And what is the weight of this path? It's the sum of the weights of the constituent edges. You take the weight of V1 to V2, V2 to V3, V3 to V4, and Vk minus 1 to Vk, and just add up all those weights. That will give you the weight of the path. Okay. So an example is this graph, which is just a single path from V1, V2, V3, V4, V5, V6, V7, V8, and V9. And you are given these edge weights. And yeah, so it says no edge weight like this. We just assume this weight to be 0. Okay. So what is the weight of this path? We just add up all these things. 3 plus 2 plus 0 plus minus 5 plus 4 plus 1 plus 6 plus 4. It works out to be 16. So a shortest path from U to V is a path of minimum weight from U to V. Right? So there are many different paths which are going from U to V, as you can see here. And let's say this red path has the minimum weight among all of these. This path has, let's say, weight 9, some other path has weight 15, some other path has weight 12. So we want to output this particular path. And the challenge is, how do we do that? The shortest pathway from U to V is defined as the minimum weight of a path from U to V. And there might not exist any path. It is not necessary that you have a path like this from U to V. It may not exist, and you want to check for that condition as well. And in case if no such path exists, then we want to output infinity. Okay. So yeah, I think it's very clear what the problem is. And this is the second problem we're looking at, which is the single source shortest path problem. Again, the same setting, which is you are given a directed or undirected graph G with non-negative edge weights. Okay. So there might be restriction on certain edge weights. There we were looking at real valued edge weights. Here we are strictly focusing on non-negative edge weights. And one problem which we saw before was given S and T, find the shortest path from S to T. Now the single source shortest path, we are given S and we want to find the shortest path from S to all other worlds. And in this lecture, we will restrict our attention to directed graphs. Okay, so we always assume that the graphs have directions on them. So why is that sufficient? Because undirected graphs can be reduced to directed graphs. So any ideas how this reduction will work? Hello.
અરે તું શું મોકલાય છે મેસેજમાં મને? હું ફોટા પાડીને મોકલાય મેસેજ મોકલાવે આખો તો ક્લિક કરું ને લિંક ઉપર. એમને કહે મેસેજ કોપી કરે આખો. મને મેસેજ જો લિંક ઉપર ક્લિક કેવી રીતે કરું? જો બતાડું.
Hello.
આવું થાય સવારે નેટ સ્લો જ આવે. એવું
So we can assign two edges between U and V.
મોકલે તું મને. પછી આનો બીજો
Okay.
ભાગ નીચે છે જો. લિંક ક્યાં છે? લિંક ઉપર ક્લિક કેવી રીતે કરું? અરે નીચે કરને પણ. બતા ક્યાં છે લિંક?
Okay. So yeah. So obviously the obvious idea, as one of you has suggested, is that and the way to do it is, let's say we have this undirected graphs, right? Uh, so there are no directions on these edges, and from this undirected graph, we can easily consider this directed graph. Okay. Let's say in the undirected graphs, you had an edge from U to V. Now in the directed graphs, you will have two edges, U to V and V to V, all of the same weight. So now we want to formally prove that if you are able to get the shortest path of weight W, then it will also correspond to the shortest path of weight W in the undirected graph. And we also want to make sure that it shouldn't be that there is some path of weight W, but there is no other path of weight W in the directed graph. Okay. So one direction is easy to see. Let's fix some path in the undirected graph. Then let's say it's going from U to U1, U1 to U2, and U2 to UK. Then you can just follow the directed version of this path in this graph. Okay. And the converse, which is, let's say you had some path of certain weight, okay, then you can also get an equivalent thing in the undirected graph. Okay. So it's fairly easy to see that we replace each edge UV by UV and VU. Okay. So we will just denote these directions by ordered pairs of vertices. So if I say UV, that means there is a directed edge from U to V. If I say VU, that means there is a directed edge from V to U. And in fact, this reduction works fine. So now, as we'll move on to the course, it's not like we are given a problem and you have to output within some specific time. It may not be completely obvious. So we need to reduce it to certain other problem, which we already know, and then use the solution to that problem. This will particularly be concept of reductions will be particularly useful when we move on to complexity theory. Okay. So now we want to focus on some special case, which is that all edge weights are unique. Okay, that means all the edges, their weights are 1. Okay. So and you want to find the shortest path from S to T. So how will you solve this? Any idea? Yeah, we want to find that. How will you find that? Find the minimum number of edges from U to V. You already know an algorithm to solve this. Short the vertices. Okay. And then what do you do? Because I want the length of the shortest path as well. It's not just I want to decide whether there is a path from one vertex to another. I want the length of the shortest. Yeah, you are almost there, but okay, fine. I'll accept that answer. You just apply a BFS. Okay. Some people also suggest that we'll use minimum spanning tree, but that only gives reachability, whether you want to check whether from S to T, and it gives some problems when it comes to uh, so because there might be something. So if you construct a minimum spanning tree here, This is a sort of counter example to that. The green edges are your spanning tree. But anyways, I think nobody suggested this. So the obvious way is to run some graph search algorithm. And one idea is to use BFS, breadth first search, right? Breadth first search is what do? You start with the start vertex S. There are certain levels, vertices on level 1. Those are at distance 1. Level 2, those are at distance 2, and so on. So it's a very obvious strategy if all the edges are of the same weight at 2 of weight 1. Okay. And it is a linear time algorithm, which is takes time just big O n plus n. Number of n is the number of vertices and m is the number of edges. Okay, so we know at least one algorithm for solving the shortest path problem if the edge weights are 1. But we want to move to more difficult cases, which is that, let's say I'm given integer weight, edge weights in the graph. Okay, you are given this source vertex S and what do you have? You are given this vertex U, you are given this edge weights, all of them are integral weights. So now what do? How do you find the shortest path? Any ideas? So we have all these edge weights 5, 6, 8, 9, 4 to 12, and we would like to find the shortest path from S to U.
Hello, sir.
Yeah.
Sir, we can look up is a greedy approach, like from starting the vertex X S, we have
Okay.
2 length 5 and 9. So we will take the minimum of that. So we will go through 5
Okay.
like that. So we reach at
Okay.
the topmost vertex
Okay.
at the top level. Now again we
Okay.
will check whichever is the less. We will go through that. So we will reach U.
Okay.
So
So
we
you are
have
suggest.
the
Okay. Okay. So
yeah,
every time you will take the minimum weightage. So as I understand, you will just pick the first minimum weightage, that is 2. Or no, you are starting from S. So the first minimum
yeah,
weightage
yeah,
is 5. And
yeah.
then from this vertex again, you will take the minimum and then you will so proceed.
Yes, sir. Yes.
Okay. Yeah. Okay. So I'm not yet in greedy stage yet. Uh, Actually, there is a much simpler algorithm. You don't have to do this necessarily. Is that you are given this graph, right? We already know how to solve when all the edge weights are 1. Okay. So
Yes.
what you can do it is, if this edge weight is 5, you bring this dummy vertices, 4 dummy vertices, and each of them is of length 1. This way you can reduce it to a slightly larger graph, but uh, all of them will have edge weights 1. Okay, and now you just find the shortest path using DFS, and you can easily do that in this particular graph because all the edge weights are 1, and it's fairly easy. And the thing to notice is, if these edge weights are bounded by something, you will only have some constant times larger graph. Okay? So there is a simple BFS based solution, and it runs in reduces to unit weight problem, which you can just solve by applying breadth first search or whatever, depth first search or breadth first search. Any graph search algorithm should work. Okay, and what's the running time of this? So what is the maximum number of new vertices you are going to introduce in this graph? It is this particular edge of weight 12, right? You have to introduce 11 new dummy vertices here, each of weight 1. And that should do the job. And so now this graph will have m into L edges, because L is the maximum weight of this graph, and you multiply it by the total number of edges, right? Because for each edge, you can have L many new edges now in this new graph. And once you have this, you just apply breadth first search, which will take ml plus n. Right? Okay, ml is the total number of edges, and n is the number of vertices. But this simple algorithm does not work because if this maximum weight could be anything, I don't know. It could be 100, it could be 1000, and so on. So we can't afford to use this simple algorithm every time. But if the edge weights are small, then you know a solution using breadth first search. And why this breadth first search works is because it has using the property that every subpath of a shortest path is an optimal shortest path. Later we'll go to dynamic programming and we will see that this property is particularly useful. Every subpath of a shortest path is an optimal shortest path. So how do you prove this? Let G be a directed graph with non-negative edge weights and distance SV be the shortest path from S to V. Okay, let's say this is our path, and we want to show that if I go from S to some Vi, then this particular path is also the shortest path from S to Vi. And the distance from S to Vi should be at most equal to the distance from S to Vk. Okay, and proving this is not too difficult is because let's assume that this was our big path, which is going from S to Vk, and let's call this vertex Vi. And let's say that this S to Vi path is not the shortest. So there is some other shortest path from S to Vi. Okay. Then we will follow that path and then go from Vi to Vk. That will be a shortest path on S to Vk instead of going via this long route. And right? So it's fairly easy to see that any subpath of this shortest path will also be a shortest path. For any such vertex S to Vi, this will be the shortest path from S to Vi. So that's what I mean by saying that any subpath of a shortest path is also a shortest path. And that is why this breadth first search strategy works. And now we'll move on to greedy, exactly the idea mentioned, which is from a given source vertex, find the shortest path for all vertices. Okay. So what we want to do here is that we maintain a set S of vertices whose shortest path distance from S is both. Okay. So at every iteration, we have this set of vertices from which we know that this is the shortest path from S. Okay. And at each step, we'll add to S some new vertex whose distance estimate is minimal. Okay. So at every iteration, there will be some vertex for which we know the shortest path length. There will be some vertices for which we don't know the shortest path. And at every step, we want to increase the size of this set by one or more. Okay. And we just update the distance estimate. Okay. And this is known in theory as Dijkstra's algorithm. Quite useful. And it uses this greedy paradigm. And okay. So let dv be the shortest distance from S to V. We will denote, and we also want, we are not just interested in finding the shortest path from S to V. We also need to output that path. What is the exact path which we want to use, right? Because it's useful in this Google Maps kind of applications where it just doesn't tell you what is the distance from Ahmedabad to Gandhinagar. It also shows you the exact route, right? So for that, we need to store this parent of V, which is the vertex which is coming after V and in that particular path. Okay. So we are going to output the exact path. Let's say for each vertex, initially we don't know. We have not done anything. So for we'll start with source vertex. And if you want to go from the source vertex to source vertex, you don't have to do anything. So we'll set the distance to be 0 in that case. And for every other vertex, we don't know anything. Let's just set it to infinity initially. Okay, these are the initial weights I'll be giving. Source vertex will get weight 0. Everybody else will get weight infinity. And then we store all these vertices in the priority queue. Okay, some kind of priority queue. Actually, you should tell me what we should use as our data structure here. Okay. So I'll just state the algorithm first, and then we'll see which data structure will give the fastest running time. Okay. So while queue is not empty, we'll just look at the minimum value in this priority queue. Okay. So all the elements are indexed by this D of V. Okay. Initially we have this 0, this is all infinity. So initially we will extract S from it. Okay. And then we do this relaxation operation, which is that you look at all the neighbors of U. Okay. So what happens here is that if we are given some value given by this, let's call it dv, right? So we have all those tests set to it. So one way is to go from, first you go to S to U and then follow the edge from U to V. That is why we are taking all V as adjacent to U. Okay? And if this value in dv is strictly larger than this particular value, then we will just store the distance of V to be du plus wu. So this is known as the relaxation step. So you relax that particular edge instead of where we will take the minimum. We want to reduce these values of dv, right? Initially we had those set to infinity, and now we'll look at every neighbor, go from s to that particular neighbor, and then just follow the edge from q2. Okay. And parent of v, which is the vertex immediately before v, that is u, that will store as the parent of v. Okay. So this is slightly different, and in fact, the idea which was mentioned doesn't quite work out. Okay, because there might be some case that we start with the minimum weightage. Uh, let's call it 2 here. No, not 2. It's edge weight 5. But it could be possible that once you reach B, now from B to the end vertex, you can't go anymore. Okay, but you had picked some larger weightage, let's call that 10, and from A to U, you can reach that edge. So you would prefer going to the larger weightage, right? So that simple greedy strategy doesn't work. So we have to do something else, which is that we set S uh, distance to be 0 and everyone else to be infinity. Now you have multiple choices. You just can't go by the weight of particular edge here, that I'll pick the minimum weightage. Okay. So that is why we go via this particular strategy, which is S to 0, A to infinity, B is infinity, C is infinity, D is infinity. Everybody else gets infinity. This S gets 0. Okay. And now we want to reduce these values so that uh, uh, it becomes some finite value and it is the smallest possible. Okay. So that particular greedy strategy where we are going from the shortest weight possible, that works only for undirected graphs, but directed graphs, it is a problem. Okay. So initially we have set S to 0 and now we want to update the others. Okay. So we will look at what is the minimum weightage going from S. It's this edge 5. Okay. So we'll add distance from S to S and then follow this edge from S to D. Distance from S to S, we have set it at 0 and 0 plus 5. So distance of B will be set to 5. Okay. So this infinity will be replaced by 5 and the parent of B will be set to S. Similarly, there is an edge from S to A. Okay. And we'll set this to 10. Okay. And in fact, for sure, we know that uh, whatever is the minimum weightage from S to B, this is going to be the shortest path, because any other way you go from S, it will give some vertices which are going from going using larger weight edges is not going to work. Okay. So you can delete B from your set and store it somewhere. Okay, S comma B. So we know the shortest distance from S to S. We know the shortest distance from S to B. And now we'll traverse the neighbors of B. Okay. So let's look at this example again. So where can you go from B? So you can go to A, you can go to C, and you can go to D. Okay. So you need to update the shortest path length to A, shortest path length to C, and shortest path length to D. And that's exactly what we'll do now. So let's say A gets updated to 8, C gets updated to 14, D gets updated to 7. Okay. And the idea is that D is the minimum now. So we need to check that some of these weights are the shortest path length. Okay. So we are know for sure that D you cannot get a weight better than 7, because what happened here is that we found the vertex which is closest to S, that was B. Then we are finding the vertex which is closest to B, that is D. So you cannot get a shorter path from S to D. Okay. And then you keep on doing this, and let's say now we have finished with B and we have finished with D. Now you traverse the neighbors of D, right? So you go from S to D and then follow the edge from D to C. So that will get updated, and for C you will get a shorter weight path, which from 14 it gets updated to 13, let's say. Okay. Now only two vertices remain, A and C. Okay, we have got rid of S, B, and D, and the shortest among these two is A, which is the length 8 path. So we'll go from S to A and follow the edge from A to C. That let's get updated to 9. Okay. Finally, we are done. We have all these edge weights, and we also get the table. Okay, because we have stored these parents here. Okay. So let's say I want the path from S to A. Okay. So the predecessor vertex of A will be B, and the predecessor vertex of B will be S. So I get a path from S to B to A, which is the shortest path. Okay, so I hope this algorithm is fairly clear. And using this table, not only do you get the shortest path length, but uh, you also get the, what you call, the exact shortest path. Okay. So any questions so far? So we need to analyze the running time. I'll do it. Let me just share one more, right? Okay, so this is what the algorithm is finally. Initially, we stored the distance of S to 0, and for each vertex, we set this distance to, which is different from S, we set it to infinity, and the parent is just store it as nil because we don't know any path here, so there is no particular path. And then we set this priority queue to the set V, and we found the applied this extract minimum operation to find the vertex with the shortest D value. And then we just applied this relaxation operation. If dv is greater than du plus wuv, we'll set dv to du plus wuv. Okay. So what's the running time here? So notice that this priority queue might get filled up with the different vertices, and this will run for big O of n times. So we are using this extract minimum operation because we want the minimum value in that priority queue, and there are some decrease key operations. Okay, because initially we had infinity, then we reduced it to some finite value, then reduce it further. So we'll use this decrease key operation in that case. And we are traversing the adjacency list, which vertices are adjacent to a particular vertex. Okay, so that thing will go on for order of m many times, and this works for big O of n many times. So big O of n extract minimum operations, and big O of m decrease key operations. Okay, so which data structure are we going to use? So there are many different options. Okay, and in fact, first we'll prove that this algorithm is indeed correct. So initially distance of S is 0, distance of V is infinity, and we would like to uh, say that dv is at least the distance of S to V for all u to V, and this invariant is maintained over any sequence of relaxation steps. Okay. Okay, so let's stop here. We will carry on with the correctness part and running time part. Meanwhile, just think about this. What data structure are we going to use here? So any questions so far?
Sir, what
Yeah.
topics are remaining till mid-sem?
So yeah, we'll have both. I think this will be until the shortest path thing.
And
So
sir,
essentially,
paper
we will just
pattern will
so that is objective. So mainly we have just seen two things, right? Divide and conquer and this greedy paradigm. Okay? That
yes,
will
sir.
be the syllabus. Yeah. So yeah, it could be more than one choice correct. Objective exam.
Okay, sir. Thank you.
Yeah.
नेगेटिव मार्किंग होगी
No negative marking. I don't think it's a good idea. There's no negative mark.
Okay, sir.
Code-based questions or theory-based? I don't know what you mean by that. Code-based questions. It could be a mixture of both. No, no partial marks. Because either you get the idea or you don't. So okay. If there are no more questions, we'll stop here. What is the extract min procedure? Okay. Let me just yeah. So extract min is just you are given this priority queue and you want to find the minimum element in this whatever set S. Okay, minimum value of D. So you know how to find the minimum, right? You can use some heap and just apply that extract minimum. We are trying to find the vertex with uh, yeah, we are trying to find the vertex with minimum. It's correct. Okay, let's stop here. Doesn't seem to be any more questions.